Welcome back to our deep dive into the world of the OEIS.
It's great to be back.
You know, that incredible online encyclopedia of integer sequences?
It's a treasure trove, really.
It is, and today we're taking a closer look at A000133.
Ooh, this is a good one.
It is, especially for our number theory students out there.
Absolutely. This sequence is like a bridge connecting the seemingly simple world of Boolean functions
Right.
to some really powerful concepts in abstract algebra.
Okay, so let's start with the foundation here. A000133 is all about the number of Boolean functions you could have with, say, n variables.
Right.
But before we get too far, can you remind us what a Boolean function actually is?
Sure. So a Boolean function,
Uh-huh.
it takes inputs that are either true or false,
Okay.
and it spits out an output
Okay.
that's also true or false. Think of those basic logical operators.
Yeah.
Or
Familiar stuff.
those are classic examples of Boolean functions.
Yeah, like if both of our inputs are true for that and function,
Right.
then our output is true as
Yeah.
well.
Exactly. Now, here's where things get really interesting. The number of these functions just explodes as you increase those variable sets.
I can imagine.
And a 000133 shows us this growth beautifully.
Yeah.
We start with 2, then 5, then 30, then boom, a huge jump to 2288.
Wow.
And it keeps climbing from there. It gets astronomically large.
So the more variables we throw in,
Exactly.
the more potential combinations you get.
Precisely. More trues and falsies mixed up.
And that just sends the number of possible functions through the roof.
It really does, and there's actually a formula to calculate these numbers. It uses exponents, which gives you a hint of just how fast these numbers grow.
Oh, I bet.
But what's really key here is that this formula is derived from Burnside's lemma. Now, this is a powerful tool from group theory.
Burnside's lemma. Okay, that sounds a little intimidating.
It might sound complex at first,
Yeah.
but the idea behind it is actually pretty intuitive. Burnside's lemma helps us count distinct objects when there's symmetry involved.
Okay, hold on. You're saying that just by flipping trues and falsies, we end up with the same function? That doesn't seem quite right.
But that's the beauty of it. See, in the world of Boolean functions, our symmetries are things like negating those inputs or outputs.
Ah.
So, for example, the function a and b is essentially the same as not a and not b, if you just shift your perspective a little. Burnside's lemma elegantly takes care of these symmetries when we're trying to count those truly unique Boolean functions.
Okay, I'm starting to see how this gets complex fast. But for someone who's deep into number theory, why should they be excited about this? It seems a bit far from prime numbers and divisibility, right?
That's a great question. While A000133 might appear disconnected from traditional number theory at first glance,
Yeah.
it actually provides a concrete example of those abstract algebra principles in action. And understanding these principles is crucial for diving deeper into advanced number theory,
Okay, I see that.
like the connection between Boolean functions and finite abelian groups, for example.
Can you elaborate on that connection a bit? I'm curious how groups come into play here.
Certainly. You see, the number in A000133 for a given n, it also represents the number of subgroups within a specific kind of finite abelian group. These are groups where the operation is commutative. We call them elementary abelian groups. And in these groups, every element sort of undoes itself. You combine an element with itself,
Right.
and you're right back to the starting point.
Interesting. So there's this one-to-one correspondence between these subgroups and those unique Boolean functions for that.
Precisely.
So by studying these seemingly simple Boolean functions,
Yes.
we're indirectly peeking into the properties of these special groups. That's a pretty neat connection.
Exactly, and it highlights how seemingly different areas of mathematics can intertwine in surprising ways.
I love that.
And here's another fun fact. Burnside's lemma, while attributed to Burnside,
Right?
it was actually known before he formalized it. Cauchy and Frobenius had already worked with similar concepts earlier.
It's a good reminder that mathematical discoveries often have this rich and interwoven history.
Absolutely.
Speaking of connections, where should we go next in our exploration of AA000133?
Well, let's dive a little deeper into how these Boolean functions are actually constructed.
Okay?
You know, we know that A000133 gives us that total number for a given n.
Right.
But can we actually picture what these functions look like?
That's a good point. It's one thing to talk about counting them,
Right?
but it's another to actually see them in action.
Exactly. Let's start with a simple case. Let's say n equals 2,
Okay?
meaning we have 2 input variables.
Right.
Now, A000133 tells us that there should be 5 unique Boolean functions for this case.
So with 2 inputs, each being either true or false,
Uh-huh.
we have 4 possible combinations:
Yes.
true-true,
Right.
true-false,
Uh-huh.
and false-false.
Exactly. That's 2 times 2, or 2 to the power of 2.
Right.
Now, for each of those combinations, our Boolean function can output either true or false. We can actually visualize this using what's called a truth table.
Truth tables. Ah, good old truth tables. I remember those from my early logic courses.
And they're really handy here as well.
Okay.
A truth table lets us represent all the possible inputs and outputs of a Boolean function.
Okay.
For our two-variable case, we'd have a table with 4 rows, one for each input combination.
Gotcha.
And a column for the output.
Right.
Now, to create a Boolean function,
Yes.
we decide for each row whether that output is true or false.
So we have 4 slots to fill.
Uh-huh.
Each with either true or false.
Exactly. 2 options per slot.
Okay, so that gives us 2 times 2 times 2 times 2.
You got it.
Or 2 to the 4th power.
Which is
16.
16 possible ways to fill that truth table.
Well, wait. Our sequence A000133 says there should only be 5 unique Boolean functions for n equals 2.
Ah, good catch.
Not 16.
You're absolutely right. And this is where those symmetries we talked about earlier come in.
Oh, right.
You remember those symmetries that Burnside's lemma helps us with?
Right.
A lot of those 16 truth tables,
Yeah.
they actually represent the same function.
Okay.
Just with those trues and falsies flipped around in the inputs or outputs.
Ah, I see. So we're basically collapsing those 16 possibilities down to the 5 truly unique functions by considering those symmetries.
That's exactly it. Very clever, right?
Yeah, very clever.
If we go through the process of identifying those symmetries, we'll find our 5 unique Boolean functions for n equals 2.
And these include some familiar faces, right?
They do, like and, or, XOR, that's the exclusive,
Yeah.
and their negations as well.
Right. Okay, I'm with you so far.
Good.
So as n increases,
Yeah.
we get more and more input combinations,
Uh-huh.
more rows in our truth table,
More rows, more possibilities.
and that number of potential Boolean functions just skyrockets.
It does. If we move into n equals 3,
Okay.
meaning 3 input variables,
Right.
our truth table would have 2 to the 3rd power, or 8 rows.
So that's 2 to the 8th power, or 256 possible ways to fill in that output column.
Exactly. But
Yeah.
again, once we use Burnside's lemma to account for those symmetries, that number shrinks down to the 30 unique Boolean functions.
Which is what A000133 predicts?
Exactly.
Okay, so we have this concrete way to visualize Boolean functions using truth tables.
Yes.
And this powerful, albeit somewhat abstract, tool in Burnside's lemma
Powerful tool.
to help us count those truly unique ones.
You got it. It's this fascinating interplay between the concrete and the abstract.
I like that.
And for our number theory enthusiasts out there, this is where things get even more interesting.
Okay, you've got my attention. What kind of connections are we talking about?
Well, one connection is to the number of subgroups of certain finite abelian groups.
Okay, hold on. Let's unpack that a little bit.
Sure.
We know what groups are in general,
Uh-huh.
but what exactly is an elementary abelian group?
All right, so picture a group where every element kind of undoes itself.
Okay.
You combine it with itself,
Right.
and you're right back to the identity element. That's the essence of an elementary abelian group.
Okay.
Now, how does this connect to Boolean functions?
Right, that's the question.
Well, it turns out there's a direct one-to-one correspondence between the number of Boolean functions and the number of subgroups in these elementary abelian groups.
So for a given
Yes.
each unique Boolean function
Uh-huh.
can be matched up with a unique subgroup of that elementary abelian group of order 2 to the n.
Precisely, and vice versa.
Okay.
It might seem a bit abstract at first,
Yeah.
but it points to this deeper structure connecting Boolean functions and group theory.
So by studying these seemingly straightforward Boolean functions,
Uh-huh.
we're kind of indirectly exploring the world of these special groups.
That's the idea. It's pretty cool, isn't it?
It is pretty cool.
And there's even more.
Oh.
A000133 also connects to concepts like rings and ideals.
Yes.
For example, it relates to the number of ideas in a Boolean ring with n atoms.
Wow, so from this one sequence, A000133,
I know, right?
we're finding links to all these algebraic structures,
Yeah.
groups, rings, ideals.
It's remarkable.
It really highlights how interconnected these concepts are.
It really does.
This has been quite a journey so far.
It has.
What else can we learn from A000133? Wow, we've been on quite the journey with this A000133 sequence.
It has been quite a ride.
Who would have thought that counting true and false combinations
Right.
could lead us to such a deep mathematical ideas?
It's a beautiful example of how interconnected math really is.
We started with these Boolean functions.
Yeah.
And then Burnside's lemma helped us navigate those symmetries.
Powerful stuff.
And now we're seeing these connections to group theory, rings, even ideals. It's a lot to take in.
It is. But it's exciting, right?
It is. So for our number theory students listening in,
Yeah.
as we wrap up our exploration, are there any key takeaways you want to emphasize?
Absolutely. First, I hope our listeners have gained a deeper appreciation for combinatorial thinking. This idea of combining elements in different ways and seeing how things explode in terms of possibilities, it's a fundamental concept.
Not just in number theory either.
Right. It pops up everywhere in math.
Yeah, it's like a reminder that even simple systems can be surprisingly complex.
Exactly. And the second takeaway I want to emphasize is the elegance and utility of Burnside's lemma.
It's not just some theoretical tool, right?
Definitely not. It had practical applications.
Yep.
It helps us understand and categorize complex structures by accounting for those symmetries. And that concept, it comes up again and again in mathematics.
It's like a lens.
Yes.
That lets us see past the surface and find those hidden patterns.
You got it. And finally, I hope that by exploring A000133, we've encouraged our listeners to dig deeper, into those connections we've uncovered between Boolean functions and abstract algebra.
It's in those unexpected links where the real magic happens.
Exactly. That's often where we find this really exciting mathematical discoveries.
So for all the number theory students out there, don't be afraid to embrace abstract algebra.
I agree.
It might seem a bit daunting at first.
Sure, but it's worth it.
As we've seen with A000133, those concepts can really deepen your understanding of number theory.
Well said. And remember, resources like the OEIS, they're just full of inspiration.
Oh, yeah.
Keep exploring those sequences, dive into the links and references,
Right.
and you'll discover a whole universe of mathematical beauty and interconnectedness.
Absolutely. Well, thanks for guiding us through this deep dive into A000133.
It's been my pleasure.
Until next time, happy exploring, everyone.